Okay. So if we were to talk about the difference between a local max and min, which is what we've been finding using our sign chart, and an absolute max and min, what do you think the difference would be? If it's absolute, what do you figure that means? Exactly. There would be absolutely no other point anywhere on the graph that would, if it's an absolute max, that could have a bigger y value than what that is. That's why it's absolute. Local means we may have all kinds of curving going on, and so we may get a maximum because we have all the points on either side of that where the y values would be less, but there could be other y values somewhere else on the graph that are bigger than that one. Absolute means there's not ever any y value that would be bigger than that one anywhere on the graph. Absolute min would be the same thing, except there's no point that would be any lower. As long as you have a closed interval, remember the example we looked at a minute ago that was the application problem that said as long as your advertising dollars were between 25,000 and 54,000, that's a closed interval because you're not going to go below 25, you're not going to go above 54. You have to have an absolute max and an absolute min. Wouldn't that make sense? The only way you may not have an absolute max or an absolute min is if it's not closed and basically your x values can go from negative infinity to positive infinity. Does that make sense? Okay. So if it's a closed interval, then here's what we would do. We would not only run our first derivative test to find what the possible critical values are, what those are, to run our test to see if we've got a sign change. But we would also use our endpoints as critical values, and we would also consider those. And basically what you'll have to do on a closed interval is you don't even necessarily need the calculus other than finding those critical values in between your endpoints. You're just going to plug them all into the original and see which ones have the biggest y value and which one has the lowest. Okay? So if it's a closed interval, after you've identified your critical points, use those and your endpoints and just plug them into the original and see what values you get back. Now, on something that it's not a closed interval, because the domain is from negative infinity to positive infinity, here's a better way that you can figure out if you've got absolute extrema. You would run a second derivative test on whatever you came up with as your local maxes and your local mins. Remember, your first derivative test is going to give you where those local max and local mins could occur. And then run your second derivative test. As long as the second derivative is a positive number, you've got an absolute minimum. If your second derivative is a negative number, then you've got an absolute maximum at that value. Okay? So finding absolute extrema on the closed intervals, you're just going to plug in. After you've identified those critical values, you're going to use those in the endpoints, plug it into the original. But if it is something that is from negative infinity to positive infinity, we could use the second derivative test to kind of be a shortcut. Let me just mention there's sort of another way you could do that to determine absolute max and min if it's polynomial in nature. Remember how we can look at end behavior on something that's polynomial? If it's odd, one side's going to go down and the other side's going to go up. Is it possible to have an absolute max or an absolute min? No. If it's odd, there will be no absolute max or min. If it's even, then you will have one absolute max or one absolute min, depending on what the ends are doing. So that's just kind of another way you could test it. We're going to see how this second derivative test works. Okay? All right. So let's see if we can find absolute max and absolute min for this function on the given interval. So they've given us something that's quadratic, and it's a closed interval. How are we going to go about seeing what, first of all, will we have an absolute max? Will we have an absolute min? And we know that why? Because it's a closed interval. So let's do this. Let's find our first derivative, which is, can you take the derivative of 3x squared? You get 6x minus 12. And then, of course, the derivative of 17 is 0. So that means if I set that equal to 0, I can factor out a 6 from this side. I'd have x minus 2 in parentheses. Where is my only potential max or min going to occur? At x equals 2. So what I'm going to need to do is to find out the value in the original function when x is 2, when x is negative 1, and when x is 8. Because those are the only places that I can have a max or a min, okay? So let's find f of negative 1. If I go back to the, remember, now I could do the sign analysis to see whether it's supposed to be a max or a min, but it's not going to tell me if it's absolute unless I go back and I actually start comparing these with the endpoints. So if I plug negative 1 into the original, I'm going to get 3 times negative 1 squared minus 12 times negative 1 plus 17. What does that equal if you clean it up? I believe that's 32. Y'all double check me on that. Does that make sense? Okay. What do you get if you plug 2 into this function? We'll have 3 times 2 squared minus 12 times 2 plus 17. Can I calculate that real quickly? It's 5. Good. And then f of 8. We'll have 3 times 8 squared minus 12 times 8 plus 17. This one you might want a calculator for. I'm getting 113. All right, so what does this tell you? All right, so I'm going to have an absolute max at the ordered pair 8, 113. And I have an absolute min where? 2, 5. That's it. Just list them as an ordered pair, because if they ask you for an absolute max or an absolute min, it's a point. You got to give both the x and the y value. So you already have it because you did that to run the test when you have closed intervals. Now on the next one, we want to see if we have an absolute max and or an absolute min. And this one is a rational function. So the first thing I should notice is, since it's rational, do I have any restriction on my domain? Because we saw a moment ago that there were certain, we had vertical asymptotes, and those values were not in our domain. Are we going to have any vertical? Okay, you're shaking your head no. Why do you know that, Derek? Exactly. Nothing can make this denominator 0. If I square any number, it's positive, and a positive number plus 1 will never be 0. So I don't have any restrictions on my domain. Now, to find the critical values, I would need to do what? Well, if I were graphing it, I could go in and find intercepts off of this original function. But if I'm looking for critical values, am I working with the original function? I got to find the derivative. So let's find f prime of x. I think let's just leave it using the quotient rule and see what we get. So tell me what we would write down first. The bottom, which is x squared plus 1 times Derivative of the top, which is 2x. Good. Now I need what sign? Minus. Then I write down what? Yeah, I could write down the top, which is the x squared minus 4, times the derivative of the bottom, which would be 2x, and all of that is over what? Bottom squared. Okay, let's do a little cleanup. If I distribute, I get 2x cubed plus 2x. Now, here, if I distribute, I've got 2x cubed minus 8x in parentheses after I distribute, but there's a minus sign in front of that. So if I distribute the minus sign through, I get a minus 2x cubed plus 8x. And what's going to happen to those 2x cubes? They cancel. And I have 10x over x squared plus 1 in parentheses squared, right? Okay, so I'm looking for any possible values of x where this first derivative could be 0. And where's the only place that could potentially occur? Well, the denominator we said can't equal 0, but the numerator can, right? So if 10x equals 0, when x equals 0, that's my critical value. Now, because this is not a closed interval, what I want to see is, first of all, I need to make sure I got a sign change there. Because if I don't have a sign change there, it can't be a max or a min. So let's finish off this first derivative sign chart. We'll put 0 on here. I'm going to test it with a -1 and with a +1. Okay? And I'm testing in my derivative. If I were to put in a -1 for x, would you agree I'd have a negative on top? 10 times -1 is a negative. But what kind of sign do I always have on the bottom? Positive. So I have a negative to the left of 0. Now if I put a +1 in for x, that's going to give me a positive on top over a positive on bottom. Do I have a change in signs? I do. So what does that tell me? This is a what? If I go from negative, decreasing, to positive, I know at a minimum, this is a local min when x is 0. Now, how can I tell if it's going to be absolute? You remember? Well, I put it into the original to actually find where the point is. So if I plug it into the original, let's go ahead and do that. Looking back at my original function, which is right here, if I put in 0 for x, what am I going to get back for y? Zero squared is 0. 0 minus 4 is a -4 on top over what's in the denominator? And -4 over 1 is a -4. So I know that's a local min. What I want to figure out is, could it also be an absolute min? Here's the way you can test to see if it is an absolute min. We could use that second derivative test. Now, I will tell you, because this thing is already a fraction, using that second derivative test means I'm going to have to use the quotient rule, or I'm going to have to use the product rule, and either way, I've got a chain rule going on here, because notice what's in the parentheses has an x squared with it. There is one other thing that I could look at. I know that this thing has the potential, well, can I figure out if I've got any horizontal asymptotes? Let's do that, because that's going to tell me what's happening on the ends. The only time I know I don't have an absolute max or min is if one thing's going toward positive infinity and one thing's going toward negative infinity. Okay? What do you notice about this? If I expanded this denominator, okay, to see if I have a horizontal asymptote, if I'm checking for a horizontal asymptote, I know I've got negative 10x on top over, if I took x squared plus 1 and I square it, x squared times x squared is what? X to the 4th. Now, I know there's other terms, but I'm only interested in the first two terms. If I have a negative 10x on top and I have x to the 4th on the bottom, what do you notice? What's happening here? Yeah, I've got 1 for the exponent on top, 4 for the exponent on bottom. Which one's growing faster? And if the bottom's growing faster than the top, do I have a horizontal asymptote? Is there a limit there? What's it going to be? Is that the Chinese problem? Yeah, it sure is. So I'm going to have a horizontal asymptote at y equals 0, which is my x-axis. Okay, so here's what that tells me. My y values on the ends are going to be numbers that are really close to 0. All right? If this is already at a negative 4, is that going to make it an absolute max? I mean, an absolute min. It is. It is also an absolute min. And I know that because this thing had a horizontal asymptote at y equals 0. All right? I could have done the second derivative test, and I would have ended up with a positive value. And as long as it's a positive value, that means that it's going to be an absolute min. Okay? All right, and let's do one last example. This one is actually number 6 on your sheet, and I'm just going to write it down here. You're going to test to see if there is any kind of absolute, and let's change that to minimum, on the interval from 0 to positive infinity for this function, f of x equals 3x to the 6th minus 18x to the 4th. Now, one reason that I wanted us to look at this one is, first of all, it's not quadratic and it's not rational. We've already looked at a number of those. What I want to ask you, first of all, on this is, using what we know about end behavior, can you tell me what should be happening on the ends for this? They're doing the same thing, and you know that because this exponent is an even number. And since the coefficient is positive, what are they both doing? Both up or both down? That is correct. Does that make sense? Now, as long as they're both up, does that mean the potential for an absolute minimum exists? Yes, it does. So, to go about finding it, let's go ahead and find our first derivative. So what's going to be the first derivative of 3x to the 6th minus 18x to the 4th? 3x to the 6th becomes 18x to the 5th minus, now let's differentiate 18x to the 4th, 72x to the 3rd, right? Okay, I need to set this thing equal to 0. And did we get lucky? Does 18 divide into 72 evenly or not? Oh, wow. Okay, that's nice, because then I can factor out an 18, and what else can I factor out with it? X to the 3rd. And in parentheses, then I would have x squared minus 4. Can I do something with x squared minus 4? It's a difference of squares. So I factor that into x plus 2 times x minus 2, and I have how many different critical values? I have 3. X can be 0, because I said 18x to the third equal to 0. When I solve that, x could be 0. What else could x be? A -2 and a +2. Now that's 3 potential critical values. Do I need to check all 3 of these? Look at your domain restriction. What does your domain restriction tell you? You're only looking on what interval? From 0 to infinity. And is 0 included? No, because it's a parentheses, not a bracket. So I don't need to worry about 0. I don't need to worry about -2. They're not in the domain. My only possible value for an absolute minimum is going to be where +2 is. So what I can do at this point, I could finish the first derivative test just to see if there's a sign change, but I already know because of in behavior, it would have to be an absolute minimum if it is an absolute minimum. And according to this second derivative test, f double prime of x, let's go ahead and differentiate the 18x to the 5th minus 72x to the 3rd. Take this first derivative and take the derivative of that. Now 5 times 18 is 90, so we'll have 90x to the 4th minus 72 times 3, good, 216 x squared. And now all I need to find out is what happens if I use 2 in the second derivative. I'm not checking for concavity. I don't have to do a sign analysis here. I just need to see, do I get back a positive number or a negative number when I plug in 2? Tell me what you get back. You get back a positive number, don't you? And if it's a positive number, it's greater than 0, and if it's greater than 0, we have an absolute min, and I would have to take 2, plug it back into the original function to see where that occurs. If I plug it into the original, you should get back a -96. You can double check that and make sure that's what you get.